K-means clustering, which is a brilliant, simple technique that has been around for many decades, and you can do it with very weak computers. And it is quite effective. All right, so let me just start with this. I installed scikit, learn just a different Python library that was the one that was recommended for this job. I'm just following a tutorial I found somewhere, of course. And we're going to make a data set. And the data set is going to consist of clusters of dots, because the main purpose of this algorithm is to sort data into categories. And this is a common unsupervised learning technique. Oops, I probably shouldn't have. I guess it's smart enough not to run this one until that one runs. We're going to see. Pip's dependency does not take into account, well, let's see. That's good. There we are. Good. So it worked. So what I've got here is just Gaussian randomness with a center and a mean. So I have 3 groups here and then 2 big groups over there. And the idea is to just sort these things into categories. And this is, by the way, an extremely common problem. For example, you can have like a marketplace like Amazon, where people go there and buy stuff like shoes and books and things. And then you say, what shall I recommend next to my customers? Well, what would help is to sort them into categories. How about the ones that buy games, the one that buy books? Now, you could predetermine that, but it would probably be better to let the data guide you and plot all the things they bought and then say what clusters exist. Probably those clusters will be something you'd understand, like young men, old women, married couples and things. But even if you don't understand exactly what makes them clusters, all you care about is here's a group of people that's certain to buy certain things, and therefore I can guess what to recommend for them next. So that's a very common problem, that you have data and you want to find the clusters. So what k-means does is this. There we go. Let me get this one running. Okay. What k-means does is you choose how many groups you want to find, and it randomly places the starts, just randomly. And what it does is it just assigns, after it chooses a placement for the representative of this group, it takes all the dots that are closer to this x than the other x's and assigns them to that group. So that's what the color does. And then it does the same for each of these. And then all it does is it takes the average of all these dots to find the position, and then does that over and over. So if your original start is not too bad, these things will fall down like a ball on a trampoline, just following down a hill, and they'll fall into optimized selections, as you can see here. Now, one problem with this is it just takes the distance between these. So notice it takes this group and it halves the distance to this group. But logically, that's not really right, because this group has a much higher standard deviation than this group. It doesn't have any capacity to handle that. So this is an issue of scaling. All the groups are treated equally, even though if you had some better system, you'd realize this group is at a different scale than that group. But it doesn't have that ability. Anyway, it is very simple. Here, the algorithm is very simple. And this one should show the steps. There we are. So if I run this one, it should show me the first several iterations of this. Iteration 1, 2, and 3, which will help make it obvious how it works. All right, here we go. So at first you start with centroids, randomly distributed. This is obviously terrible. You have put 4 of them on the left and only 1 on the right. So now you label the instances. You take this one, and you just take the dots that are closer to that one than this one and label them. So you see, it does a pretty bad job here. It gets some of the ones that belong in this cluster, but some of them are assigned here. But it's going to get fixed, because this will move to the center of the ones you labeled yellow, which will move it just a little bit here. This one will move to the center of the things it found, which are really bad, but you see there's a cluster down here, so it will move in that direction. It will move closer to the center of that one. And now you color them again. Now this is actually getting pretty much the right dots. These 2 are straightening out, and this one, as you can see, is making progress towards the right center. So they're going to converge pretty nicely. So that's and this is a really simple calculation. All you do is take the distance of the dots to the centroids and figure out which category they're in that way. and then just take the mean of them all. So it's really pretty simple. So that's pretty nice. Now the problem is, if you have bad starting values, if you choose the initial centroids really badly, just by bad luck, then you're going to have, this is never going to converge. It's going to get some dots here and some dots there. I'm never going to have more than 2 groups here. I'm going to split this group in half, and this one in the middle is never going to figure out it should go all the way over here. It's just going to bounce around there, so you're going to end up with a solution like this, which is pretty bad. You split this group in half, and you combine these 2 groups into one. So that's the flaw of a bad starting value. Now, for that reason, the actual algorithm tries 10 random starting values and takes the best of them. By the way, you have a measure of how wrong it is. This is the mean squared deviation from the center, so this should be as close to 0 as possible. And you can see these ones, the best fit was only minus 220. Up here, I was able to get down to 212. That's a good fit. So the fact that it couldn't get any closer to 220 is a clue that even when it converges and stops changing, it hasn't actually done a very good job of categorizing these data sets. And another issue, of course, is how do you know there were 5 categories in the first place? And that turns out to be a little difficult to do automatically too. And as I mentioned, the fact that these things have different standard deviations is not included in the model, and that's a defect. And like we did in a previous one, if you just expand the vertical scale by a factor of 10, that's going to have a bad effect too, as you can imagine. Now you're telling it that vertical distances are 10 times more important than horizontal distances, so it's not going to be willing to fit a round Gaussian sphere to it. So what you're going to find, let's run this one. All right, the same data, where the solution would be nice Gaussian distributions. Uh-oh, it doesn't like something. That's interesting. Xperi is not defined. Oh, I skipped a step, that's why. Up here is where I expanded the scale. Okay, so I had to run this first. All right. Now, one crazy thing about Colab, by the way, is you can run the blocks out of order. It remembers the result of each block. So when I run this one, it's going to remember I've defined those variables, and now I can go back and run this one. That can get you in trouble. I've had this happen. All right, but anyway, now it runs. There you are. And so this is what it thinks the solutions are now, because you told it vertical distances are 10 times more important than horizontal distances, so this is now the logical grouping. And you're completely failing to solve the problem because of a difference in the scale. So that's a fundamental problem with almost all these machine learning models. The scale, the relative scale of the axes matters, and you may very well have to scale your data. Typically, an early exercise in every machine learning model is to first scale all the data so it goes from 0 to 1 or something, unless you have actually some reason to think that one parameter is far more important than another. So now we can do this one, where again I had sort of an argument with the textbook I got this out of. So we make it a data set that is not so simply breaking up into groups. We make the moons. So here we are, we got blue and green. So we'd like to separate this into 2 categories. Now the problem is it only has 1 centroid. So it's going to be pretty bad at doing this. But if what we do is let it have 8, then it will do this. It'll break them into 8 categories. And the book said, this is a terrible fit. And I said, well, I don't think so. This is actually, I call this pretty good. I'd add a second layer that says, interpret all these as green and interpret all those as blue. This is one way to do it. It doesn't do it all in one step, though. I mean, it's broken your 2 categories into 8 categories, but that's about all it can do. Anyway, all right, and now it turns out to be extremely useful. Here's an example of how useful this can be. Here, if you have a digits data set, we got the time. Let's go through this one because I really enjoy this one. Let's clear everything out. I'm gonna, I'll just delete them all up here. Okay, so now, by the way, that does not remove their effect. Those variables that were previously defined, I think they're still in memory. A thing to be aware of. Anyway, so now I'm going to make another data set of digits. These are just handwritten digits, so there they are. Here's the first 50, and there are a lot of these digits. There's 1,400 of them, but I'm just showing you the first 50 of them so you can see what they look like. They're handwritten digits. All right, and they're labeled, so I do know the right one. 8, that's a 4, 1, 7, and so on. So it's a labeled data set. But suppose it was not labeled. But we're going to get there. This is why we're going to benefit from this. So first we'll fit a model to the entire training set. So we have 1,400 points, and somebody has actually gone to the bother of making humans label all 1,400 points. So we can now train a model, and when we do, we can check the model. So we train it on 1,400, and we take the remaining ones and test it on them. So I guess there's even more than 1,400 of these, and there's the answer. So the end result is we're getting a 90.68% success rate. So by training on 1,400 labeled models, we get 90.68 chance correctness on the, oh, I should zoom into this. I see my zoom in doesn't work in this zoom. All right, we get 90.68% success. So that's using all the data. Now, suppose we only used the first 50 instances to train it. Then you would suppose that would got to be inferior. So let's try that. We train it on now we're only 75% correct. So as you'd expect, if you only learn from the first 50 examples, you don't learn as well to really capture the population. All right, now what you do is we're going to use k-means to make 50 clusters. We're going to take all those images and group them into clusters using k-means, 50 of them. So there are 10 possible images, but there are probably various different ways to shape them wrong. And now we're going to print the examples that are closest to the center of each of the clusters. So rather than having 50 randomly assigned data points, just the first 50, these are the 50 that represent the center of each cluster. So these are like here's a 7. You could make it crooked. You could put a cross in the middle. These are all the ways that 7 is drawn. And now what you do is humans manually label them. So here, I manually labeled them, and 937 looks good. All right. So now if I manually label only those examples, so I only pay for humans to label 50 of them instead of labeling all 1,400 or 2,000 or however many there are, and now I train on just those 50, then I move from 75% up to 85% correct. Because instead of training it on a random 50 images, I have carefully chosen the most representative 50 images that are in the center of clusters that appear to capture the mean shape of it. But you can do even better. Now that I've labeled those 50, I can assume that all the ones in the k-means cluster around that centroid have the same label. So I can now propagate those labels to all instances and then train on that. So this is a way to multiply the power of my human trainers, my human categorizers. And when I do it, I get up to 89% correct. Now, so I remember that I had 90 point something correct when I trained on all 1,400 labels, so I haven't caught up with that. But what I have to do now is remove the outliers. Now remember, up here, when I made these k-means clusters, even when it worked pretty well, if I go to the one, I have a good solution like this. This is fine, and this is fine, but what about this point up here, and these points over here? Do I really believe this point is gray, and this point is green? I probably don't. I don't know what category these are in. It probably is not really helping me to assume that this point is in that category, and this point is in that category. It would be a lot better to just remove these categories, these items on the edge, because I really don't know what label to assign to them, and the label I've assigned to them is probably wrong. So that's the next step to improve this thing. You propagate the labels to all the outliers, to all the points in each group, and then you remove the outliers. You take 1% of the ones that are furthest from the center of the cluster and remove them. So I get back to here. So when you do that, and see, I have a cutoff, so I'm going to keep only the 99% that are closest to the centroids and throw it. Now I actually do better than training on the original labeled data. I get 90.9% instead of 90.6%, which is, of course, within the noise. I mean, logically, there's no way that this procedure could be better than training on the original data set in principle. But if you overtrain on the original data set, that might explain why this is better. This is getting the real signal and not as much of the noise. Anyway, that's what I want to show you. That's actually a reason why even a problem that does not appear to be a clustering problem might actually be solved using clustering algorithms. This is a way to do it. And again, I can see a lot of application for this for guessing what product to recommend to a customer, or guessing which customers are most likely to return a product or have a problem. You know, you could take a group of students and predict what cluster of them are doing fine, what cluster of them would benefit from help, that kind of thing. You could have medical data, and you could figure out which ones of these diagnoses appear to be wrong. You know, I have x-rays or blood tests or something, and I have a group of people that are correctly diagnosed and moving along, and here's people where there's something wrong with the diagnosis. The data doesn't really seem to fit with the diagnosis that came from the physician, so I probably should send these people for further examination, that sort of thing. All right. Anyway, that's what I wanted to show you. I'm going to stop.